Let's move on and talk a little bit more about gravity. Gravity is a really strange force. In general, it's incredibly weak compared to other forces. If we compare, for example, the force of gravity compared to the force of a magnet, the force of a magnet, which is relatively small, is much more than the force of the entire Earth. Remember, what gives us weight is the whole of the mass of the Earth pulling us downwards. And yet we can fight that force very easily. We can use the muscles in our own body to jump up in the air and get away from the force of gravity. So the force which attracts positive charge to negative charge, which is ultimately where we get the power in our muscles from, is much, much powerful than gravity. The force of magnetism is also much more powerful than gravity. So the force between everyday objects is so tiny, only just measurable in the lab, that if we want to understand the force of gravity, if we want to see how gravity works with masses or gravitational fields bigger than that of the Earth, we have to go out into the universe, where there are much more massive objects, where there are much more dense objects, and much more powerful gravitational fields. So what do we find when we study gravitational fields so much more powerful than the Earth's gravitational field? Well, let's think a little bit more about how gravity works here. When I throw an object up into the air, usually it will come back down. And you may have heard that what comes up must come down, but actually that's not quite true. If you throw something up into the air hard enough, you can actually throw it hard enough that it will escape from the Earth's gravitational field entirely. It will just keep going and going and going out into space. So if I throw this apple up in the air at a bit more than 11 kilometers a second, then in principle it'll just keep going and going and going. Now let's imagine that the Earth is the same size that it is now, but we're going to increase its mass. What happens then? Well, we'll all feel very much heavier. In fact, if we double the mass, we'll feel twice as heavy. And the speed that we would have to throw this apple in order to escape the Earth's gravity would be much, much bigger. Eventually, if we increase the Earth's mass by a huge amount, we reach the stage where I would actually have to throw this apple up at more than the speed of light in order for it to be able to escape. Now we know from experiments that we've talked about before that light is affected by gravity. Light is bent as it moves past the sun. So what we would have if we had an object which was the size of the Earth but with a huge amount more mass, so a much, much more dense version of the Earth, is we would actually have a mass that was powerful enough to suck in light. And what's more, if you were on the surface of this object, it would be absolutely impossible for you to escape. So this hypothetical object, which has a mass or a density so great that it can actually trap light, is called a black hole. And by applying our theories of gravity, we can understand in a great deal of detail how such an object would affect the things around it. Well, here's an intrepid explorer who wants to see what it's like inside a black hole, and so they dive in head first. They're attracted towards the black hole. But because the force of gravity is so powerful, and remember the force of gravity depends on how far you are away from the mass, their head is actually pulled harder than their feet. Initially, this would just feel like a little bit of a strange sensation of being stretched. But as they get closer to the center of the black hole, it begins to pull harder and harder. And eventually, there'll be nothing left of our intrepid explorer than a long ribbon of matter. And in fact, it doesn't matter whether we have an intrepid explorer or anything else. Eventually, any matter which falls into a black hole is going to be stretched. It's going to be pulled particle from particle into a long ribbon of matter. And we call this process spaghettification.